Hello everyone, my name is Huaduo Wang. I'm currently a PhD student of UT Dallas. My co-author is Gopal Gupta. We will introduce a new inductive learning algorithm for learning default rule for mixed type data that includes both numerical and categorical values. FoldR is an automated inductive learning algorithm for learning default rules for mixed data. It generates an explainable normal logic program rule set for classification tasks. We will show an improved FoldR algorithm, called FoldR++, that significantly increase the efficiency and scalability of FoldR by orders of magnitude. FoldR++ improves FoldR without compromising or losing information in the input training data during the encoding feature selection phase. The FoldR++ algorithm is competitive in performance with the widely used XGBoost algorithm. However, unlike XGBoost, the FoldR++ algorithm produces an explainable model. FoldR++ is also competitive in performance with the Ripper system. However, on large datasets FoldR++ outperforms Ripper. Why do we need explainability in machine learning tasks? Generally, machine learning models are complicated and find it hard to explain their decisions and actions to human users. The training data may not be correct or have biases that baked into the learned model. It could lead the model to make wrong or biases predictions. The training data may not represent all the possibilities so that the learned model make discrimination predictions against disadvantaged. Even if data is representative of all aspects, we still don't know if the learned model is fair and unbiased. The only way to know is to expose the internal logic in the learned model. Also, we want to explain to the end user how the model makes decisions. The GDPR in Europe requires companies to explain. And there will more regulations for explanation of machine-made predictions. The users may also want to know what to do to flip the decision delivered by the model. Here is an example. John is a bank customer, and applies for a loan. But his application gets rejected. John needs to know why. The bank executive needs to know the reason too, perhaps to make business-related decisions. But the model is a neural network and uninterpretable, and the data scientist cannot provide a justification. These responses leave John and the executive unsatisfied. Explainability of a model, therefore, is very important. It can help refine the learned model, and expose the deficiencies in the data. Our approach is to generate defaults rules as the learned model. Default rules with exceptions can closely model human thinking process. Common sense knowledge can be represented easily with default rules. We will use answer set programming, an extension of Prolog, to represent the default rules. Here is an example of a Prolog program. We have the fact that Jim is John's father. Mary is John's mother. John is Rob's father. And Sue is Rob's mother. We also have definitions representing rules. X is Y's parent if X is Y's mother. X is Y's parent if X is Y's father. X is Y's grandparent if X is Z's parent and Z is Y's parent. X is Y's ancestor if X is Y's parent. X is Y's ancestor if X is Z's parent and recursively Z is Y's ancestor. Given these rules, we can ask queries, for example, is Jim the ancestor of Rob? The answer is yes. Or, we can ask the query, find the individual A who is Rob's ancestor. Our algorithm outputs default rules with exceptions. The default logic can express the facts that are true in majority of cases but not always. For example, birds normally fly. Or, by default birds fly, but there are exceptional birds that do not fly. In the rule set 1, AB0 means abnormal case 0. It can be translated as follows: normally, a bird flies, unless it is a penguin. In the rule set 2, we assume that there exists some super penguins that can fly. So, super penguin is an abnormal case of a penguin. This rule set can be read as follows. First rule says, birds normally fly but penguins are exceptions. Second rule says, penguins are abnormal birds that cannot fly, but super penguin are an exception. Default rules can be realized in answer set programming, which is prologixed with negation as failure. Answer set programming can reason with incomplete knowledge and can model human thinking. The fold algorithm by Farhad Shakarian is inspired by FOIL algorithm and is the basis of our new algorithm. Like the FOIL algorithm, the fold algorithm incrementally select the best literal from residual training examples till it fails to find one. The fold algorithm first learn default literals incrementally, then it next swap positive and negative examples and calls itself recursively to learn exception to the default. It continues this process to learn exceptions, then exceptions to exceptions, and so on. It finally merge all the learned default and exceptions to produce the final rule set. Here is an example of fold algorithm. The goal is to learn who can fly from the training data. B represent background knowledge. X is a bird if X is a penguin. Tweety and Woody are birds. D is a cat. And Polly is a penguin. The positive examples of birds that fly are Tweety and Woody. And the negative examples are Polly and Kitty. The candidate literals are bird, cat, and penguin. First we need to find the best literal based on their information gain. The first selected literal is bird. It provides most useful information among the candidates but still wrongly implies a negative example Polly. We cannot find next literal for default because the information gain of all other literals are 0. It's time to swap the residual positive and negative examples to learn exceptions. We start to learn the first exception rule. For now, the positive example is Polly and negative examples are Tweety and Woody. The literal selected is penguin. It can perfectly divide the positive and negative example. So the learning stops. And the learned exception case is if X is a penguin. There is one default rule and one exception rule in the final rule set. The final rule set can be translated as X can fly if X is a bird except when X is a penguin. In a tabular data set, there are usually numerical values and categorical values. Mixed-type data that include both numerical values and categorical values are very common. Both types values can appear in the same row or even the same column. Missing values and special marks are also common in most of data set. The left picture is kidney disease data set. There's a question mark on the second column while rest of the values are numerical. The right picture is Titanic survival data set. There are many missing values in the table. Most of the machine learning model can take only one type of data. Mixed data need to be processed before training. Generally, there are three methods to handle mixed data. First method is one-hot encoding that discretize numerical values into independent categories. It loses the greater and smaller than relation for numerical values. Second method is label encoding that encodes categorical values into integers. It adds non-exist greater than or smaller than relation to categorical values. It is wrong in most cases. Third method is to discard mixed-type data records. This leads to information loss, especially when most of examples are mixed-type. Our new algorithm fold R++ generates two types of literals for different features. The fold R++ has its own comparison assumption to deal with mixed data. First type is equality comparison literals for categorical features. With this kind of literals, two values are equal if they are same type and identical, else they are unequal. Second type is numerical comparison literals for numerical features. To compare two real numbers is straightforward, but the numerical comparison between a numerical and categorical values is always false. With the comparison assumption, the literals in the generated rule set are able to handle the mixed type values directly. Here is an example of the comparison assumption. The equality between 3 and A is false. The numerical comparison between 3 and A is always false. Another example is to illustrate how to evaluate a literal with specific values. The positive examples 1, 2, 3, 3 have been classified into true positive category because they are smaller or equal to 3. The positive examples 5, 6, 6b have been classified into false negative category as 5, 6, 6 are greater than 3 and the numerical comparison between b and 3 is false. The negative examples 4, 6, 7 have been classified into true negative category because 4, 6, 7 are greater than 3 and the numerical comparison between a and 3 is false. The negative example 2 has been classified into false positive category because it is smaller than 3. Both the fold and fold R++ algorithms employ information gain as heuristic to guide the literal selection. Fold R++ speeds up the literal selection by using prefix sum technique. With prefix sum, the best literal of a feature can be selected with only one pass of classification for the training data. This is a simplified function for information gain. We only calculate the conditional entropy part because the entropy of the same data would be exactly same. Here is a prefix sum example. Given positive and negative examples with mixed type values for feature I, the target is to find the literal with the best information gain on the given feature. The table on left side lists the positive and negative examples. The prefix sums are calculated in the table on right side. The value A and B do not have prefix sum. The prefix sum table only need to be calculated once and can be used for the heuristic calculation of all candidate literals of one feature. For example, the information gain of literal, value smaller equal to 3, is calculated with parameters 4441 and the result is -0.619. The information gain of other features can also be calculated easily. The algorithmic details are in the paper. Here is an example of the Titanic survival dataset. The task is to make prediction for survival status of unseen examples. A tuned rule set learned by the fold R++ algorithm captures the underlying pattern of the data. It's easy to translate to natural language. The 0 in survived predicates means X perished. The underlying pattern is: male passengers perished. Female passengers in third class perished. Who paid fare less equal to 23.25. We did some minor improvements in code, so the time cost is better than the numbers on the paper. Here is the latest result. To compare with original fold algorithm, our new approach is much more efficient and scalable to large dataset. It outperforms the fold algorithm in classification and explainability on the last two datasets. For the credit card dataset, fold R++ only need 4 seconds to generate about 19.1 rules to achieve 82% accuracy. While the fold algorithm need to spend 24 days to generate more than 500 rules to achieve only 64% accuracy. We also compared with XGBoost classifier. We use simple setting for XGBoost without limiting its performance. One hot encoding has been used for data preparation. The classification performance of fold R++ XGBoost is competitive, but fold R++ is more efficient and explainable. Ripper is an well-known rule induction algorithm. No encoding is needed for Ripper. For small data sets, the fold R++ is competitive with Ripper. However, fold R++ is more efficient. For the last 3 large data sets, fold R++ outperforms the Ripper algorithms in all aspects. Also, for large data set, Ripper would generate much longer rules than fold R++. Conclusion: fold R++ can directly handle mixed type data without losing information. It uses prefix sum to speed up the literal selection process. It generates much fewer rules by actively learning exceptions. It is competitive with widely used models like XGBoost and multi-layer perceptron but produces explainable solutions. It outperforms the well-known rule induction algorithm Ripper in all aspects on large data sets. Thanks NSF and ATOS for funding the development of this research.